Okay, folks, good afternoon. Another cold day in Missouri. Spring is not around the corner. First of all, a reminder, there is a homework assignment posted on Blackboard due next week on Tuesday. What I want you to do is exactly follow the procedure that we followed in our lecture, basically. Let me show you what I mean by that. What we did last time, we talked about modeling power electronic converters. And first we developed a general model for a single pole double throw switch as appears on the screen. So I'm talking about this model over here. So anytime from now on you identify a single pole double throw switch in your converter, for instance the buck boost converter that is the topic of the homework assignment, you should take that switch out and replace it with this model and then go ahead and find the transfer functions. Do not start from the equations of the converter. So the whole plan is for you guys to practice identifying a network like this, taking that part out, and then replacing it with this network. Actually, we did it already for the buck boost. So technically, you should start with this model or this circuit diagram over here. And then from here, you have to find the required voltage or whatever transfer function that is required. One thing to note is, in this class, as I have noted before, I'm assuming that this is the polarity for the output of our buck boost converter. Therefore, V out over Vn is D over 1 minus D. It is not negative D over 1 minus D, as some of the books suggest. So please remember, our voltage transfer ratio is positive, D over 1 minus D. All right. So that's about the homework assignment. Let's talk about the quiz. I didn't do the solution for the first quiz because the first quiz was very, very simple and straightforward. Let's take a look at the solution for the second quiz. We had it last week, just on Tuesday. As it turns out, this is actually cell K2 of that paper. I have already provided the equation that but if you are curious about what happens to the output voltage, VC2 or the output voltage over Vn is 1 minus D over 1 minus 2D. So as you can see, these both voltages, depending on the value of your duty cycle, they could be sometimes positive, they could be sometimes negative. So if duty cycle is less than 0.5, you get positive values for these voltages. If the duty cycle is larger than 0.5, you get negative values for these voltages. We are only considering. And by the way, it is mentioned that S1 and S3 are the active switches. Not that really matters. In obtaining these transfer functions, that assumption has been made. And we are only thinking about or curious about realizing these two switches over here. So for instance, case A, the duty cycle is 0.4. Therefore, this voltage turns out to be positive. Now, keep in mind the classic way that we have in mind for a single pole double throw switch is this way. The throws are on the left, the pole is on the right, the inductor is on the right, the current of the inductor is flowing from left to right, and the V throw is, the top one is positive, the bottom one is negative. There's a little bit of a twist over here because this has kind of flipped to form S3 and S4. So for this case, if I draw it in accordance with what I am familiar with, in other words, this is point A now, this is point B, and this is P. And I've already mentioned that the inductor currents are already positive, so you don't really have to worry about that. So this current in this direction is going to be negative, and this voltage is going to be positive. So we are looking at basically a fourth quadrant switch realization. So this is a fourth quadrant switch. So this would look like this. So this is A, this is B, and this is P. So this is S4, and then this is S3. And no problem in terms of S3 turned out to be a switch. S4 turns out to be a diode because our original assumption was S3 is the active switch, so no problem there. We can just command it to turn on and off. Now for the other case, which is case B. Now the duty cycle is greater than 0.6, therefore this capacitive voltage is negative. So again, looking at the classic way of representing this, so this would be negative, but this current is still negative. So we are looking at the third quadrant switch realization. So this is A, this is B, and this is P. So the current is negative. S3 is here, S4 here. Now S4 turns out to be an active switch, so all we have to remember is when you're simulating it or when you're building this, make sure that whatever command that you had to apply to S3 had to be inverted and then supply to S4, because you can't really directly command anything to S3 because it's a diode. Now for the last case, that we have a general case of D is a variable thing, so we basically have to combine, I don't know what it was, D was between 0.3 and 0.7, yeah. So this voltage could be sometimes positive, sometimes negative. But this current is still negative in this direction. So we're looking at a combination of the third and the fourth quadrant. So it's like a bottom half plane switch. I'm going to draw it slightly different than what I've drawn before. Oops. So again, this is point P, this is point A, and this is point B, and this is S4, and this is S3. Now, we need commands for both S3 and S4, but originally S3 was the active switch, so whatever signal that was available to us, we had to invert it and also apply that to S4. Any questions or comments? Okay, so this was the solution that I was expecting from you guys. All right, so now comments. Let's move on. Yes.
So it says in the instructions that S3 is the one receiving the duty cycle.
Right.
So that implies that it's the active switch.
Right.
So when I set it up, or it implies that it receives the command. So when I set up the model, S3 should be the one receiving T1, throw 1.
Are you talking about case B, or all the three?
Both, all the cases.
Okay. So ask your question one more time. I didn't understand the question.
So, in the description of the problem, it said the duty cycle is applied to S3.
Right.
So that means the command, or C, when C equals 1,
okay.
is being applied to S, so it should be throw 1. It should be S3. So B should be on the top.
Well,
Point B should be on the top.
You can draw it that way, but yeah, you can draw it that way, but that doesn't really change the whole thing that, so C is equal to 1 or not is another definition. The whole thing that when we talk about S3 is the active switch, meaning that you have to make the assumption to obtain these voltage gains. If you make a different assumption, like S4 is your active switch, then your gains are going to be different. In terms of drawing that, it's okay to assume that the bottom switch is receiving the command, but this could actually interfere with the assumption that we made in the modeling aspect. When we were making the switch realization aspect, it's okay to assume that the bottom switch is receiving the command. It doesn't really violate anything. But in terms of modeling, remember, this is a good point. Remember, when we model things, we always assume our command is applied to the top switch. When you are doing switch realization, it doesn't matter as long as you remember which switch is the active switch, which switch is not the kind of passive switch. It's okay to do that. In terms of drawing, it's okay. If you draw B on top and A in the bottom, that's fine. No problem there.
Okay, that makes sense.
Sure.
Thank you.
Sure. Any other questions? Yes.
So would they really be in series or like could it be in parallel?
What in series and parallel?
The top throw and bottom throw of.
Oh, so this is kind of with it. We were trying to combine case A and B to get case C. So here we are kind of placing this diode in series with this switch over here to get this portion. And then we were putting this, let me see if I can make it a little, okay. We were placing this one in series with this one to get basically these two guys over here.
Gives a unipolar current and a bipolar voltage.
Yes, so it is actually, in terms of current, it's unipolar. In terms of voltage, it is bipolar. Okay, any other questions? Yes?
In case 3, if we replace the S4 with the diode downstream to it,
okay.
like, does this make any difference? Or?
Oh, you are telling that we don't really need switch S4, we only need a diode.
No, I mean, when, for example, when you go from P upstream, instead of putting a diode, the S4 is...
Oh, you mean swapping these two?
Yeah.
That's fine, yeah. They are just in series. You can draw them any way you want, yeah. Oh, yeah, absolutely, yeah. That's what I said. I'm drawing them slightly different than I was drawing it in the class. So, yeah, these are two series elements. You can put the diode on top and the switch in the bottom. Is that your question?
Yeah.
Yeah, you can do that, absolutely. Absolutely. Okay, so let's move on to our lecture. What we did was, as I said earlier, we developed or we found out a kind of a small signal model for a network of a single pole double throw switch. So we started from here and we ended up with this equivalent model. So from now on, this is what I expect you guys to do, especially in the homework assignment. Then we moved on to basically representing our power electronic converter as like a controlled block diagram. We have 3 inputs. 2 of them are out of our hands. Actually, they are determined by the environment, like the variations in the input voltage, fluctuations in the output current, or the output resistance. Doesn't matter what you define as the source of variations. And then the duty cycle. Now, the fortunate part is the duty cycle we can control. So that's our control input. The other ones are considered as disturbances. We have 2 outputs in general. Technically, you can always assume that your output voltage is one of the output of the converter because you're trying to control it. But sometimes the inductor current could also be considered as an output if you're directly measuring it and controlling it. We define 3 transfer functions of GVG, Zout, and GVD. GVG highlights what happens to the output voltage if the input voltage is perturbed, and GVD highlights what happens to the output voltage if the duty cycle is perturbed. So this is the overall block diagram, and what we are going to do today is we are going to try and find a controller. What is a good transfer function as our controller to be able to achieve the goals that we are going to define. So as an example, what I did was I just focused on the Bode topology, and I was trying to find GVG, okay, which is the audio susceptibility. So you assume there is no variations in duty cycle, there is no variations in the output current or the load. The only thing that is changing is the input voltage. So no variations here, it's 0. No variations here, it is also 0. And so the system reduces down to something very, very simple, which is this basically, this very simple circuit. You have to solve it using, you know, the impedance network and things like that. It's a voltage divider, so we ended up with actually a GVG of being like R in parallel with 1 over CS, and then LS plus the same network times D. Okay, now let me go back and go to the new sheet. So now we are going to continue on this. So technically, we are still talking about the Bode topology. We are talking about the VG, and it turned out to be, if you kind of simplify that transfer function that I had earlier, D over so it's like a quadratic form. We expect that to happen because we have one inductor, one capacitor, so we would expect to see a second order kind of a behavior. And this D over here should not be a surprise to us, because D is actually representing the DC value of this transfer function. When S is 0, or there are no variations, or frequency is 0, or in a DC way, this transfer function turns out to be, okay, let me write it over here, GVG of S for S equals 0 is D. And this is basically what we expect to see, because if you remember, V out over V in is D. So that average or DC model that we very first analyzed for the buck converter can actually predict the DC value of this transfer function, but the rest of the dynamic is not predictable by that approach. Now, as long as this transfer function is concerned, we are good to go. We have the transfer function, we can plot it, we can analyze it, we can do whatever we want with it. However, it is more common to write this transfer function in this form. So this is a classic or canonical form of representing a second order basically transfer function. Omega naught turns out to be 1 over the square root of LC. So this is called like the corner frequency, angular corner frequency. And we're going to see why it is called the corner frequency once we plot the Bode plots, basically angular corner frequency. All right, and Q is like a quality factor. It has no dimensions, quality factor. So this is a more kind of a standard way of representing a second order system. Now, we want to plot this to have a kind of a visual understanding about what it looks like. If you have taken a control class in the past, You are pretty much familiar with Bode Plots. He was an engineer, I believe, in Wisconsin. He passed a few years ago. It's not a very old topic, basically. So he came up with some way of representing this transfer function in terms of plotting them, graphically plotting them. So in case you are not familiar with Bode Plots, we are going to have a very brief introduction of what they are. So first thing that we try to do is, remember, S is the complex number. It's basically j omega, so it's a complex function. So we look at the magnitude of this complex function. So we'll replace S, which is the Laplace basically variable, with j omega, and then look at the magnitude. So this symbol is highlighting the magnitude. So if we do so, we will end up with this. Okay, something like this. Okay, so several observations here. Usually we go to the extremes. What if omega is too small? What if omega is too large? For instance, if omega is much smaller, omega is your variable, which is your angular frequency. If we are way on the left-hand side of the corner frequency, then this transfer function has an asymptote of d basically, okay? If omega is much smaller than omega naught, this is almost 0, this is almost 0. In the bottom, we only end up with 1, and then d divided by 1 is d basically. So that's an asymptote. Then if omega is too large, if omega is much larger than the corner frequency, so technically this 1 becomes insignificant, and I think one of, hold on, there is a square here too. I have to double check my notes. I'm afraid one of these is, hold on, let me check. I'm afraid one of these is omega over omega naught. The other one is omega naught over omega. But anyway, I'll put a question mark here. I have to go and check back my notes. But anyway, this have an asymptote of d over something like this, okay? Actually, it's correct. I don't think we need this. So if omega is much larger than omega naught, then this is a very, very large thing. It is much larger than 1, so we can neglect 1. And it is, because it's to the power of 4, it is much larger even this, so we can actually neglect this. So all that ends up in the bottom is omega over omega naught, basically, squared. Okay, so now let's plot this thing. We plot it in dBs, which is like 20 logarithm of the original thing. So it ends up with something like this. Okay, so this slope is negative 40 dBs per decade. Okay, and here we have 0 dB. And this is omega naught. So that's why we call it the corner frequency, because there's like an angle happening in that corner frequency. And remember, these two lines are just the asymptotes. They are kind of representing the extreme behavior of the system if omega is too small or if omega is too large. Okay, the real transfer function could be going from here. It could actually spike a little bit here depending on the value of basically the quality factor. If the quality factor is too high, then we will see actually a little bit of a hump over there. All right. So negative 20 dBs per decade means if your frequency gets, if you go to 10 times larger the frequency, you're going to drop the gain by basically 20 times or something like that. All right, so this was the dB or the magnitude. Now we have to look at the angle of this thing as well. Okay, G. Now once you do the math, you're going to end up with this expression. Again, you can argue and see what happens if omega is too small, what happens if omega is too large, and you end up with this graph. This is like 0 degrees, negative 90, and negative 180. You have a behavior like this. Okay, again, depends on the quality factor. Let me redraw this a little bit better. Okay, something like that. So at low frequencies, this transfer function is basically like a D. And by the way, this point over here is 20 times logarithm of D, which is a duty cycle. Now, duty cycle is less than 1. Logarithm of a number that is less than 1 is negative. So 20 times that is also negative. So that's why we start from this point, which is negative, which is 0 basically. So everything is in the negative territories. So in the end, you see at lower frequencies, like let's say if your frequency is somewhere here, you get an attenuation that is close to the value of the duty cycle, and you get a little bit of a phase lag over here. Once you increase the frequency of your fluctuations, for instance, once you go to, for instance, this point, very high frequency fluctuation, you have a huge amount of attenuation, which is from here to here. This is 0 dB, and for instance, this is negative 60 dB. All right, so you get like about 1,000 times of fluctuations, and then in terms of phase angle, you get about 180 degrees of phase shift. So it depends on where you are, where the frequency of your basically perturbation is, you can actually predict what the system behaves like. If you are not familiar with Bode plots, I would encourage you guys to become or make yourself familiar with Bode plots, because we're going to use this a lot in terms of when you're designing a composition network for your converter. You use Bode plots to basically find the best composition network, like graphically. Any questions? All right. So this was only for one converter, which is the buck converter, and only one of the transfer functions of the buck converter, which was the audio susceptibility, GVG. Now we can spend hours and hours and hours find the other basically transfer functions, or we can open a classic power electronics book and find those transfer functions, which somebody has already done it, so we don't have to repeat them. And here is the table that you can find in, for instance, the book that by Dr. Erickson and Maximovich. All right. So let me draw the table, then I will tell you what these parameters are. So they have a definition which is G sub G naught, and then G sub G naught. So G sub G naught is the DC value of the audio susceptibility transfer function, and G sub D naught is the DC value of the control to output transfer function. Then they have omega naught, Q, and omega Z. And by the way, remember these are only valid for the buck converter. In other words, once you switch to another converter, your corner frequency is not 1 over the square root of omega c. And we're going to see that actually. So if you're looking at the buck converter, we are looking at the DC gain of D, we just saw that. Then this is V out over D, which is nothing but the input voltage. This is 1 over the square root of L times C, we just saw it. And this is R times the square root of C over L. And there is no omega z. I'm going to talk about what omega z is. This is actually the zero in the control to output transfer function. If you switch to the boost converter, this is 1 over d prime. Remember, d prime was 1 over, d prime is 1 minus d. And this is v out over d prime. Over L. And the last row is pretty much what's your homework assignment. So you can verify the answers for your homework assignment with this last row. And then d prime squared r over dl. Okay. So this table kind of summarizes the audio susceptibility, which is GVG, and the control to output transfer functions for the 3 classic converters that we have seen. Let me just double check, make sure everything is correct. Yes. D prime R, CL. Okay. So, in the more general form or canonical form, the control to output transfer function might have a 0. The bottom is pretty much what we introduced earlier, a classic way of representing a quadratic transfer function, and it could have a DC gain of G sub D naught. So this G sub D naught is actually introduced here in this column of this table, basically. All right, what about GVG? Again, it has a gain of G sub G naught. Nothing in the numerator, and the denominator is the classic one. Okay. So first of all, first observation, these are all second order systems. We always have two poles for both of these transfer functions. So we have two poles. GVG does not have any zeros, but GVD has 1 0 for the for the boost and for the buck boost converter. For the buck converter, that 0 is in infinity, or basically it doesn't basically exist. So for the buck converter, this whole thing is reduced down to 1 for the buck topology. Okay, just remember that. Okay. Back in the 70s, when they were developing these transfer functions, when they end up with this, they were kind of happy because this small signal model was able to predict the zeros of the control to output transfer function. I'm talking about these zeros over here. This is omega z. For the boost and for the buck boost converter. Boost and buck boost converters have like an inherent kind of a instability issue, and that is being explained. I'm going to talk about it in a few minutes by this 0. The other thing that I want you guys to remember is there is a negative sign over here, meaning that this 0 is on the right half side of the complex plane. So it's a right half plane 0. Okay. So these zeros are right half plane. Or RHP. Okay, and we're going to talk what's the right half plane 0, okay? The system is still stable. Is there a way to verify these transfer functions by, for instance, if you have a hardware, because this is pretty much based on a bunch of assumptions and a bunch of approximations. Yes, there is. If you, for instance, have a network analyzer, you can actually inject a particular harmonic into your system and measure the response of your system to that particular harmonic, and point by point kind of sweep these transfer functions and actually plot them, and they are very, very pretty much close to what we already have in an analytical form. Now, this column is very, very easy to remember because it is nothing but the gain of your converter. So the buck converter has a gain of basically D. So this is V out over V in. So technically, when we started analyzing converters at the beginning of the class, we looked at the steady state behavior, DC analysis. We were pretty much covering the first column of this table. Now, as you can see, the book that I was just mentioning, the book by Dr. Erickson and Maximovich, in that book, for the buck boost converter, they have actually assumed the opposite polarity for the output voltage. That is why there is this negative sign appearing here. So please pay extra attention to this negative sign. All right. However, the homework assignment that I assigned to you is the opposite of this. So technically, your last row should be very close to this. Your answer should be very close to the last row that we have, with the minor difference that you're assuming that your output voltage is positive. In other words, your voltage gain is D over 1 minus D. It is not negative, D over 1 minus D, okay? So this is because this is the polarity for the capacitor that you have assumed is this way. right? Something like this. Okay, so this is a canonical form of representing these two transfer functions for the three converters. What about the output impedance? A lot of times output impedance is neglected, and we will talk a little bit about the output impedance later. But pretty much with these two transfer functions, we can design the compensation network that we would like to have. Now, before we get to the designing a compensation network, let me talk a little bit about this right half plane 0. So if you at some point hear that the boost converter has an instability problem, or the buck boost converter have an instability problem, it goes back all to this omega z, which is a right half plane 0. So let's talk a little bit about that. If you have taken a control class, you know that a right half plane 0, if a system has a right half plane 0, the indication is the system is a non-minimum phase, basically, system, or has a non-minimum phase 0. Okay, what does that mean? So let's just look at a very simple transfer function. Well, this system doesn't really exist in reality, but in basically mathematics, you can pretend that it does exist. So let's say we have a system, and in that system, we have a right half plane 0 at frequency of omega z, okay? So let's look at the Bode plots of this guy. So as long as the magnitude is concerned, it is pretty much like basically a left half plane 0. It doesn't really matter. The polarity of the 0 doesn't matter, but the angle matters. Okay, so if I plot this, okay, let me redraw this. Move to the right. Okay, so it's like that, something like this. Okay, the magnitude of G. So at very low frequencies, it basically has a gain of 1 or 0 dBs. At high frequencies, then it has like a gain of 1 over omega z, something like that. And this is pretty much like a right half plane 0, exactly the same behavior. I'm sorry, like a left half plane 0. However, if you look at the angle, it behaves like a pole. So if you remember from a classic control class, what was the Bode plot associated with a 0 versus what was the Bode plot associated with a pole, this right half plane 0 is like halfway between. In terms of magnitude, it behaves like a left half plane 0, no problem there. In terms of phase angle, it behaves more like basically a pole. meaning that it adds extra negative phase delay in the system. That's why it's called a non-minimum phase is basically 0. And that extra phase angle that is provided in the system or induced in the system may potentially make the system unstable or may force you to be very conservative when it comes to designing the compensation network, and therefore the bandwidth should be very, very small. And we are going to see that later. I'm just basically trying to introduce the topic a little bit here. All right. If you want to have a physical understanding about what a right half plane zero is, let's make a simple system like this. As I said, these systems do not really, exist in reality, because remember, systems should be causal, and this is not a causal system. But I'm just trying to oversimplify this. So you have an input, and then you have an output. Okay, so your transfer function is 1 minus s over omega z. S is like, you're actually taking the derivative of your signal. So you are taking the derivative of your signal, then dividing that by omega z, then adding it with with a negative sign, dividing it with a 1. So this is the transfer function we're looking at. So at very high frequencies, remember, S is j omega. High frequency means S is too large. So S over omega z gets too large. Therefore, it's much larger than 1. We can actually neglect 1. So the indication here is at very large frequencies, there is a negative sign which relates the input and output changes. So the input and output voltage, the input and output of the system are going the opposite directions, basically. So that's why it's a non-minimum phase system. So for instance, you're trying to increase your output, but the indication is you have to decrease your input to increase your output, something like that. Okay. And this sometimes tends to destabilize the system, because in a general sense, when you increase your output in input, you would expect your output to increase as well. So, but they're actually going the other way around. But this is only happening at high frequencies. Now, do we have an example for a very high frequency excitation in the system? The answer is yes. When you, for instance, apply a step change into your system. A step change is actually if you look at the frequency spectrum, it represents a very sudden change or very high frequency change in your system. Going back to the boost converter, if you are concerned about, or if you are curious about, how come the boost converter have this issue and the buck converter does not have this right half plane zero? So let's take a look. So if you are looking at a boost or a buck boost, and your converter is running at 0.4 as the duty cycle, or 40% duty cycle. and all of a sudden you change that duty cycle to 0.6. Okay. The output voltage that you're going to observe generally speaking, remember in all of these converters, if the duty cycle increases, the output voltage also increases, right? Like in the buck converter, V out is D times V in. So if the duty cycle increases, V out increases. And in all of them, 1 over 1 minus D or D over 1 minus D. But here, because it's a non-minimum phase system, all of a sudden you have applied a sudden change. It's a very high frequency change. The input and output go opposite directions. So the output actually decreases a little bit and then increases ultimately. Okay, something like this. So this is the non-minimum phase behavior. So at the very beginning, your overall objective is to increase the duty cycle, and therefore your output voltage should increase. But at the very beginning, your output voltage actually decreases a little bit. So it goes the opposite of what you intend to happen. But in the buck converter, that doesn't happen because you are not looking at a system with a non-minimum phase thing. Okay, something like this. If you look at the schematic of these converters, you may be able to actually justify it. So let's say all of a sudden I want to increase the duty cycle. That means the switch should be on for a longer portions of time. If this switch is on for a longer portion of time, you are trying to energize the inductor actually with more energy. That's good. That means ultimately you want to deliver that energy to the load. But if the switch is on for a longer period of time, the diode is not conducting as much. Therefore, the capacitor is going to get discharged more through the load without being charged. So you can see that all of a sudden the output voltage may actually decrease instead of increasing. But ultimately it will increase because ultimately you're going to open up the switch and that energy is going to be delivered to the load anyway. So you can see there's a bit of a time delay. You want to increase the energy that is being delivered to the load or the power that is being delivered to the load. But because you want to do so, you have to keep the switch on more often or for a longer period of time. That means first we have to basically energize the inductor here, then the energy is being released. They are not actually simultaneous. Whereas in the buck topology, if you close the switch, you are actually directly delivering power to your load. There is no time delay involved. When you close the switch, you are energizing the inductor. At the same time, you are delivering energy to your RC tank. In the boost and buck boost converters, it's the opposite. You close the switch, you are energizing the inductor, but you are not delivering any energy through the source. You are not delivering any energy to the load side. So there's a bit of a time delay in the boost and buck boost converters. That time delay represents itself as a right half plane 0. In the buck converter, that doesn't exist. So in the future, if you hear about this whole right half plane and instability in the boost and buck boost converters, this is where it comes from. So one of the early signs, or basically, yes, question.
Can you please explain me through this technique how the frequency matters there?
How the frequency matters, frequency of the perturbation, you mean?
Yeah,
Okay.
the omega, when it's crossing the omega z.
Why omega z is important?
Yeah. When we are considering that thing, like capacitor is discharging more.
You mean here?
Yes.
Here omega z doesn't matter. The absolute value of omega z doesn't matter. It's just an indication on like high frequencies, what constitutes high frequencies, what constitutes low frequencies. Omega is basically creating a border between those two, basically high frequency and low frequency. But in reality, it doesn't really matter what omega z is. As it turns out, if you do a numerical analysis, going back to this table, L is a very small number compared to your resistance. Like L is in the order of Henry, Henry and things like that. But your load resistance is, for instance, 10 ohms. So if you numerically evaluate this is a very high frequency right half plane zero. Okay, it's not a very low frequency, and actually a good thing. It's a very high frequency right half plane zero. However, if you get to a case that R and L are comparable, like your load is 10 ohms, but for a very weird reason, your inductor is all at 10 henries, which is not a practical thing, then you really see that omega z is actually moving to the left-hand side. So you're going to actually observe this basically non-minimum phase behavior even more often with the smaller changes and things like that. The value of omega z, potentially it doesn't really matter. Okay.
To summarize, basically, we would encounter this problem only at very high frequencies. Normal, like
you would
10
encounter
kilohertz.
these problems if omega z is a dominating. Okay, let's talk about the word dominance. Okay, and if it is a dominating zero, or if it is a dominating non-minimum phase zero, means that in terms of value, it is smaller than the other zeros and poles in the system. The good news is, a lot of times, as I said, R is much larger than L. So R over L is very large. Therefore, your zero happens at the very right-hand side of the system. Generally speaking, you don't have to be extremely careful about it. This thing that I mentioned, that if you have a step change that represents itself like a high frequency change, that is true no matter what the value of omega z is, basically. Okay. So high frequency, we don't have high frequency and low frequency changes in the system. Like a step change has a low frequency content and high frequency content. Okay. So we don't really have high frequency changes in the system. If you have a step change in the system, it pretty much has a very wide spectrum covering the system.
So if we were to look at frequencies like 10 kilohertz or say 5 kilohertz or 10 kilohertz, we should watch out for which particular factor, like d dash square r?
Yes, if you have a perturbation in the system that is only 10 kilohertz, we are going to see that for the Bode plots that we are going to have in the future, we are going to see them. This omega z does not play a significant role, okay? Because at 10 kilohertz, you are pretty much here. Your zero has not had a chance to actually create a 90 degrees of time delay, basically, okay? So this usually is in the order of like 1 meg. Or something like that, radians per second. Okay, so we are going to see this, and I can guarantee you go and simulate a boost converter, you may never see this negative hump over here, because of that ratio between R and L is too large. It is so little you can actually see it. But if you want to really see it, make your L very, very large, and R over L gets smaller, so you can actually start observing this hump, negative hump. All right, any questions? So this was a little bit of a, definition or the discussion about the right half plane zero. So I just wanted you guys to be familiar with this, because some of the power electronic converters exhibit an instability problem that is rooted in this right half plane zero, basically. So this is why I talked about it. Now let's go back to those transfer functions that we were developing and basically controlling a power electronic converter. So generally speaking, you have a converter, so, or let's say control, or let's call it feedback loop. So let's say you have a DC to DC converter, and this converter has a switch in it, obviously. And you can turn the switch on and off. That means you can control this switch. And on the output side, you always have a capacitor that holds a relatively large capacitor and holds a DC voltage. And you are connecting your load to this capacitor. Okay. And your objective is to provide a constant output voltage regardless of what is happening on the load side, what's the value of the load, what's the power consumed by the load, or regardless of what's the value of the input voltage, if it is rising or falling or something like that. So what comes to your mind in terms of doing is, you say, okay, I want to control this output voltage. The first thing that I have to do is just measure the output voltage and see where it is. Is it too much? Is it too little? So I need to measure it. So you need some sort of a voltage sensor to measure this output voltage. Now, this sensor may have its own transfer function. Okay, it could be like a low-pass filter. So in general, it's not just a number. It could be actually a transfer function. It's usually represented by h of s. Okay, once you sense this, you are going to compare it with your reference. Let's say your output voltage is 100 volts and your sensor has a gain of division by 50. So 100 divided by 50 is 2. And then your reference is hovering around 2 volts basically. So you're comparing it with your reference. To obtain the error. Obviously, if your output voltage is exactly where it is supposed to be, this error is 0, you don't have to worry about anything, you don't have to make any changes. But usually that's not the case. So this is called the error signal. Okay. Then you kind of have to process this error. You have to have a history of, okay, the error is 0 now, but what was it 1/10 of a second before, or how did it go, how quickly did it go up, or how quickly did it go down? So you need to have a kind of a compensator here. And our overall objective is to find the right or the best transfer function for this compensator. So we call it G of compensation, C. G stands for gain, and obviously C stands for compensation. So you get a voltage out here, which we usually call it the control signal. So, and usually this is a very kind of a slow-moving kind of a signal. So the level of this signal is determining what your duty cycle should be. So if your error is too large, the compensator sees this large error and decides to increase its output, meaning that the duty cycle should increase. If the error is, for instance, negative, then If the error is negative, the compensator sees that and decides to decrease its output voltage, indicating that the duty cycle should actually decrease. So the level of the signal of VC is representing kind of your duty cycle. So it's this level of the signal, you have to convert it to a duty cycle, like a pulsating signal. So you got to use a block here. It's called pulse width modulation. So you get this pulsating signal of zeros and ones. The 0 means the switch should be off. 1 means the switch should be on. Okay? And sometimes it is not strong enough to turn your switch on and off. So sometimes you also use a gate driver. Which is nothing but a power amplifier, basically. And then it is turning the switch on and off. Okay. And this pulse width modulation also has its own gain. We call it G of M, gain of modulator. Okay. All right. So let's think about it this way. So first, let's talk about this pulse width modulator. This pulse width modulator is nothing but a comparator. Okay, so internally you are generating a kind of a sawtooth waveform. If you are curious about how a sawtooth waveform could be generated, you can actually have a tiny little source of current, very constant, and then charge a capacitor. Because capacitor is integrating that current, the voltage of the capacitor gradually rises. Then at the end of your switching period, you can discharge or reset this capacitor, so the voltage of the capacitor jumps to 0. So you charge it, jump back to 0. Charge it, jump back to 0. So you're creating a kind of a sawtooth waveform. And the output would be the difference between VC and this sawtooth waveform. Let me just zoom in a little bit here. Okay. So remember, when VC is greater than, because this is a comparator, when the positive input is greater than the negative input, the output is 1 or true or something like this. Like for instance here to here. Then when they cross each other, the negative input is getting larger than the positive input. So the output of the comparator jumps to 0. Something similar here. Like in the third period or in the third switching cycle, you can see that VC has increased, the control signal has increased, therefore the duty cycle has increased. Because the signal is happening or is placed at a higher level, they cross each other at a later time, therefore the duty cycle is increased. So this is the basically output. So this very simple trick, you can convert the level of your signal, VC as your signal, to a kind of a width of a basically pulse. So if your signal is higher, your path is wider. If your signal is lower, your path is kind of narrower. So the PWM module is actually doing that. Yes.
If we like keep charging the capacitor,
Uh-huh.
will it not like infinitely become charged?
Yes, but that's we shouldn't do that basically. Yes. So if the question is what happens if we infinitely charge the capacitors, just this voltage goes up. Well, obviously there's a limitation there. You cannot infinitely charge it. Either the capacitor is going to blow or the voltage rises too much.
No, if you keep on adding charge to that capacitor and then the voltage comes back to zero, but you are actually the current integration, it will go back. Average of IC has to be zero, right?
No. Oh, no. Average of IC should be zero. You're right. The average of IC is zero. How is it zero? So let's do it. Okay. So we are talking about how we are generating this sawtooth waveform. Okay. So you have a capacitor and you have a switch, which is basically a transistor. And then you are charging this capacitor with a constant source of a current, which is a current mirror in microelectronics. Okay? So when I open up the switch, the voltage rises. When I close it, it goes down to zero and then goes up and down. All right. So the question is, the average current of this capacitor should be zero, right? How is that possible? Here is how it is. So this is the voltage of the cap. Let's look at the current of the cap. Okay. So it is positive, which is this I, right? Then it's a huge negative value, almost like a delta function. For a very short period of time, we are disconnecting this. If there is no resistance in the system, it's like a delta function. So basically it goes down. If there is a little of the resistance, it doesn't go to negative infinity. So it's like something like that. So you are right. On average, the current of this capacitor is zero. All right, so we have like a delta function going on over there. All right. So going back to our PWM discussion, so remember the job of this modulator is to convert level into width, basically. As simple as that is. All right. So let's go back here. Let's hypothetically say this is a gain of division by 50. This Vref is 2. And our output voltage is 105. Okay. So 105 divided by 50 is larger than 2, right? So you realize that this error gets positive. I'm sorry, it's negative. So the compensation network sees this negative input, VC starts decreasing. Very simple way of thinking about this compensation network is just think of like an integration block, basically. If you provide a negative input to it, its output gradually goes down. So VC goes down, pulse width. So remember, this modulator is converting level into width. So the signals are going to get narrower. Or basically the duty cycle goes down. If any of these converters that we have seen, if the duty cycle goes down, the output voltage goes down. So the output voltage goes down to get to 100 basically. So if it is more than where it is supposed to be, there is a mechanism over here to bring it down. What if it is a smaller than what it is supposed to be? Let's say it is 95. So 95 gets divided by 50. It's a smaller than 2. So this error gets positive. The compensation block sees this positive, error and tends to increase its output voltage. Again, as I said, it acts like an integration block. So the level of the signal rises, the duty cycle increases. Therefore, the output voltage increases. So we do that infinite amount of time, so the output voltage has to be exactly 100. Otherwise, wherever it is, there should be a mechanism, or there is a mechanism to actually act the opposite way, to direct it or steer it the way or the place that it should be. So I'm going to stop here. So we're going to start here next time on Tuesday and go and look at some compensation design network techniques, basically. All right, see you guys on Tuesday.